Hi folks, welcome to round 2 of related rates. Today we'll do one that involves Pythagorean theorem and then do a couple that involve trigonometry. So we've got this question here. At a particular instant, a car is 3 kilometers north of an intersection and traveling towards that intersection at a rate of 38 kilometers per hour. Another car is 2 kilometers east of the intersection and moving away from it at 45 kilometers per hour. What's the rate of change in distance between the cars? So we should probably draw this. Our steps are draw, define variables and derivatives, make an equation, don't sub yet, differentiate with respect to time, and then solve for what it is we're looking for. So let's make that diagram. We've got one car that is 3 kilometers north of the intersection. So let's say that's our intersection. Here's our car 3 kilometers north and it's traveling towards the intersection. So this could be our 3-kilometer length right here. We've got another one that is 2 kilometers east of the intersection, so it's over here somewhere, and it's traveling away at 45 kilometers per hour. So it could be right here. This will be 2 kilometers. And there's our basic diagram. The intersection is going to be perpendicular like this. So now let's start to assign some variables for each of these. For me, I would call this x because it's horizontal, and I'm only counting the length, not the direction of anything. The north-south I'd think of as y, so there's 3 kilometers. The distance between them is this distance right here, which I might call z. That is unknown at this point. Let's see what else we know from the problem, though. They tell us that the first car is moving towards the intersection at a rate of 38 kilometers per hour. So first of all, since it's a rate, it's going to be a rate of change or a derivative. Okay, so we're talking about our y's here. It's changing like this. dy by dt is going to be 38 kilometers per hour. But that's not all. Y is decreasing, it's getting smaller, so dy by dt has to be negative 38 kilometers per hour. This length would be getting smaller as this car drives towards the intersection. The other differential or derivative that we're given here is for 45 kilometers per hour. That's this other car that's driving away from the intersection. So dx by dt, or the rate of change, would be 45 kilometers per hour. Now let's ask ourselves, as that car drives away, there we go, is x getting bigger or smaller? We should be thinking x is going to get bigger. The distance between the intersection and the car would be increasing. So that's why this derivative would be positive. The thing that we actually want is the rate of change in the distance between the cars. So that would be dz by dt. That's what we want. So we've got two unknowns. That's not an ideal situation to be in. Let's see if we can fix that up. We know y and x. We can use Pythagorean theorem to figure out what z is without any calculus stuff. I'm taking my little scrap board. I'm going to say x squared plus y squared is z squared. That's Pythagorean theorem. X would be 2. Y is going to be 3. Which means z squared is going to be 13. Or z is exactly root 13. We could round it, but then we're going to get rounding errors. So let's keep it exact. In this instant, the distance between them is exactly root 13 kilometers. Draw a picture, define our variables and derivatives. Now it should not be that difficult for us to work this through. We make an equation, so we've got a right-angled triangle. That equation can be, again, Pythagorean theorem. But here I'm going to differentiate. And we differentiate in a related rates question typically with respect to time. The WRT means with respect to. So we differentiate, we're going to get 2x times dx by dt plus 2y times dy by dt. And lastly, equals 2z dz by dt. Just like in the last video, you can divide this whole thing by 2 to keep your numbers a little smaller. It's up to you whether you want to actually do that. I'm going to. But I wouldn't skip that first step because the first step really shows where the differentiation comes from. All right, let's sub in our values. We have 2 for x, we have 45 for dx by dt, we have 3 for y, we have negative 38 for dy by dt. For z, we have root 13, and that's times dz by dt, which is what we hope to find. So that's 90, and this is going to be minus 114, so that's negative 24, is root 13 dz by dt. And exactly, dz by dt is negative 24 over root 13. And we can get a decimal approximation if you really want. Now, what are the units for dz by dt? We've got negative 6.7. Z was measured in kilometers. All the lengths were measured in kilometers. And time was measured in hours. So if we want to answer the question in the end, it says, what is the rate of change in distance between the two cars? One thing that we've got to decide is, are the cars getting closer together or further apart? And that's kind of a difficult question when you've got one car moving towards the intersection and one moving away. They have different rates of speed and they have different distances from the intersection. Thankfully, it's all contained in the mathematics. This negative here, if x, y, and z are lengths, then the negative means distance is decreasing. If it had been positive, then that distance z would be increasing. So to answer the question, we'll say the distance between the cars is decreasing at a rate of 6.7 kilometers per hour. In other words, they're getting closer together in that instant. So the questions we had with Pythagorean theorem last lesson all had one side that wasn't changing. In this question, all the sides are changing, but it doesn't make it a whole lot harder. We just follow through and then make sure we interpret our answer. For our second example, let's take a trip to the theater. Let's imagine that there's some production, and in this production there's a woman in one scene who's walking in a straight path at a rate of 4 feet per second. And there's a spotlight that tracks her movement. It's 20 feet above the ground, and it's kept focused on the woman as she walks away from the base of that post that holds the spotlight. And we want to know at what rate the searchlight is rotating up or down. So this is obviously going to have to move to track her motion. When she is 15 feet from the base of the post. So she's moving along, and at some point here she is 15 feet from the base. Okay, and obviously there's a beam of light that is going to be focused on her. Let's write what we know. We know that the height of this is 20 feet. I'm going to call that y because it's a vertical distance. I know that this distance over here is 15 feet from the base of the post. I know that she's moving in this direction. And I know her rate of change of motion. She is moving at a rate of 4 feet per second. So that is a derivative that we know. What do we not know? Well, we don't know z, this over here. We don't know dz by dt. But we don't actually necessarily care about any of those things. The question says, at what rate is the searchlight rotating? So here is the angle that the searchlight makes with the post. We want to know about its rate of change. So really what we're looking for is d theta by dt. So when I look at that question, I think, oh man, there's a lot of stuff that we don't know in here. We don't know z or dz by dt. We don't know d theta by dt, but that's what we want. There might be one thing we do know, though. We know the rate at which the post is changing. The post is not changing height, so dy by dt equals 0 feet per second. Looking at these sides, this is a side we know a lot about. This is a side we know a lot about, plus it has the added bonus of having a side that is not changing at all. I'm going to have to use trigonometry to find a rate of change of this angle. So let's label the triangle in terms of grade 10 trigonometry stuff. If this is the angle we care about, then here's my opposite side, here's my adjacent side, and here's my hypotenuse over here. Side we know a lot about is opposite. So let's take a trip down memory lane to SOHCAHTOA. Here are two ratios that involve the opposite. Another side I know a lot about is the adjacent. So tangent is going to be our best choice here. It involves both of the sides we know a bunch about. If we wanted to use something that has hypotenuse, we'd have to find dz by dt. So let me set up this equation now. The tangent of theta is the opposite over the adjacent, or let's rewrite that with the letters that we have. It's x over y. And this is not referring to any unit circle stuff. On the unit circle, yeah, tangent's going to be y over x. But this is just in our drawing, it's opposite over adjacent, which happen to have these letters. Okay, in our technique, we said, draw a picture. Awesome, did it. Define variables and derivatives. Did it. Make an equation. Did it. Now the next thing is to differentiate. Generally, we said don't sub in any values. There is one exception to that. There's one case when you can sub in values, and that's when you have quantities that are not changing at all. So this y of 20 here has a derivative of 0. You actually are allowed to sub in this 20. It's a little less safe than just doing the derivative with all the letters in there, but it's going to save us some quotient rule. At the end of the video, I'll come back to this question and I'll do it without subbing in, and maybe it'll show how much easier this is. So when a quantity has a derivative of 0, you can sub before differentiating. That means in some of our questions from the last day, you could have subbed early, though there wasn't a whole lot to gain from it. Here, by subbing early, we might spare ourselves from actually having to do the quotient rule, so let's take advantage of this property. Tan theta is going to be x, which is changing, so I've got to leave that letter in there, over y, which is not changing, y is just 20. Now I can differentiate. And carefully. So this will be secant squared theta, and from the chain rule / implicit differentiation, we get times d theta by dt. This is going to be 1 over 20, but again, from implicit differentiation, we get dx by dt. That is the differentiated version of this equation. Now we just have to sub in. Now secant is the buddy of cosine. Cosine is adjacent over hypotenuse. It's right here. Secant is hypotenuse over adjacent. And you might notice that we never bothered to find the hypotenuse. Maybe that would have been a smart thing to do earlier on, but I can do it now. So x squared plus y squared is z squared, just Pythagorean theorem. 15 squared plus 20 squared rather is z squared. And that's going to give us, when we work it out, z is 25. So this side here is 25 feet. Now we're ready to sub in. So secant squared means the secant, which would be hypotenuse over adjacent. So hypotenuse over adjacent, 25 over 20, all squared, times d theta by dt is 1 over 20 dx by dt, so that was just 4. And you can use your calculator or you can do it analytically. I'm just going to simplify and work it through. I've got all my work done here. I get d theta by dt is 0.128 or 16 over 125. I might think about what my units are. This is an angle, and the natural angle measurement system is radians. So this is radians per whatever time was in, which is seconds. The other thing we notice here is that this derivative is positive. So that means this angle is increasing. It's getting bigger. And that makes sense. As the person walks this way, this angle will have to get bigger. So answering this question in context, we would say the angle is increasing at a rate of 0.128 radians per second in that instant. We'll do one more that involves trig, but just to take a little gander through the problem, we realized that we didn't know some quantities or their derivatives. Some of them it didn't matter though, dz by dt we never really needed. We found some sneaky derivatives, and we made sure that we were clear about what it is we're looking for. We're looking for the rate of change of the angle, so that's d theta by dt. We chose one of our 3 primary trig ratios to work with. We differentiated carefully, making sure we involved implicit differentiation. We subbed in, and then finally we interpreted the answer. Our last related rates question involves a trig classic. We've got a Ferris wheel that rotates at a rate of 0.2 radians per second, and it has a radius of 13 feet. We're wondering, at what rate is a passenger rising when they are 5 feet above the midline of the wheel? So passengers going round and round and round, and at a certain point, here's the midline. They are 5 feet above it. They're right at this point. Let's take a look at a demonstration. For no particular reason, I decided to put a pirate on this Ferris wheel. And there he is, going round and around, having the time of his life. Now let's freeze the frame right here where he's a little bit above the midline of the Ferris wheel. So now that we know where he is, we can start to record some dimensions. There's the midline horizontally, and you can see he's 5 feet above it. So we're going to call that y is 5 feet. The thing we're looking for is how fast y is increasing. So that's dy by dt. We know the diameter of the Ferris wheel is 13 feet, and we also know dz by dt. The Ferris wheel is not changing diameter, so dz by dt is 0 feet per second. Now we can start to think about the angle. The angle was the thing we were told something about. We know that it's changing at a rate of 0.2 radians per second, or in other words, the Ferris wheel is rotating at that rate. There are other things that we don't know. We don't know x or dx by dt. We might be able to figure out some of those things, but we also might not need to know all of those things to answer the question. Hopefully after that little demo, this diagram makes a little more sense. Once we've got it with all our derivatives defined and our lengths defined, it might be nice to get rid of the whole circle and just think of it as one little triangle that we're going to deal with. And we'll be looking for dy by dt because that is the rate of change in the vertical direction. So here's the question just distilled down to one little triangle. And what we want to find is dy by dt. And it's easy to focus on all the things that we don't know, like x and dx by dt. You can go and try and find everything, but I think it's going to be simpler for you to see if you can make do with what you have. So One thing that is worth finding is the last side. If you have two sides in a triangle, you probably want that third side. So by Pythagorean theorem, I can go off to the side and figure out that this is 12 feet for x. Now I think about the sides that I know about. I know a lot about the hypotenuse. So sine and cosine sound like good choices. And I want to know about this side over here, which would be my opposite. This is opposite, this is hypotenuse, and this would be adjacent in relation to this acute angle. Okay, so I know a lot about the opposite. I know a lot about the hypotenuse. I should use sine. If all I was looking for was the angle itself, I could use any three of them because I know all these sides. But we have to think about the derivative as well. So the sine is going to be the opposite, which is y, over the hypotenuse, which is z. Can we sub anything in? Yes, we can sub in 13 for z because that side z is not changing at all. Because its derivative is 0, it's fair game to plug it in before we differentiate. You don't have to if you don't want to, and I'll go over how that works in the last example at the end of the video. Okay, now we're going to differentiate with respect to time. With respect to time, what do we get? Sine turns into cosine. Don't forget that chain rule, that implicit differentiation. We have the sine of theta, so we need to tack on a d theta by dt. This is going to turn into 1 over 13, and again, chain rule, implicit differentiation gives us that dy by dt. Cosine. Cosine is adjacent over hypotenuse. So the cosine of this angle is going to be 12 over 13. You never have to actually find the angle itself, which is kind of neat. D theta by dt we know is 0.2 and 1/13 dy by dt. I can multiply both these sides by 13 and then have 12 by 0.2. What I'm going to get in the end is this. 2.4 is dy by dt. Its units are going to be y is in feet and time is in seconds. So at that moment, the pirate is rising at a rate of 2.4 feet per second. And it probably feels kind of exciting in that moment. Let's answer the question. We get that the passenger is rising at a rate of 2.4 feet per second. And we know that because this derivative is positive. So y is a quantity that is increasing. That brings us to the end of our investigation of related rates questions. At the end of this video, I'll tack on a little bit on how to do this kind of differentiation without subbing in your 13 first, but it is easier to put in those numbers when it is safe to do so, and it's only safe to do so if their derivative is 0. I hope you found this helpful, and good luck with the practice questions. As promised, we'll take a look at that second example, but without subbing in the value before differentiating. So here's what we got in the end was 0.128 radians per second, but we spared ourselves the quotient rule by subbing in that 20 because the derivative of y was 0. We said then you can sub in before you differentiate. But if you don't want to do that, then that's fine. It just takes a little longer, but it's probably a little safer. So we'd still differentiate with respect to time. We'd need a quotient rule. So the derivative of x with respect to time would be dx by dt. The derivative of y with respect to time would be dy by dt. And if I were to do this whole differentiation, well, this side would still be secant squared theta times the derivative of theta. This side is going to be u prime, so dx by dt, v, which would be y, minus u, v prime, which would be dy by dt, all over y squared. You can see it looks like a little bigger mess, but it's really not that bad. Secant squared is still going to be 25 over 20 all squared. I'll sub in the values. Dx by dt is 4, y is 20, x is 15, dy by dt is 0, all over y squared, which is 20 squared. And what you're going to find out is that this is 0. These 20s will divide out, so you just have 4 over 20, or 1/5. And 25 over 20 is 5 over 4, all squared. In the end, as we work this out, you'll have to square this, so you'll times by 16. 16. This will be 25. You'll divide. Same answer. And really not that much worse. But again, when you have a derivative of 0, you can sub in before differentiating. If you don't, then you may have to use some of your other rules.